Welcome viewers to the second segment of the first lecture for the online series of lectures for the course of Dynamical Systems. The last segment, towards the end of the last segment, we discussed about the sufficient condition for the existence of an integral curve, and we were supposed to discuss an example on that. Now I'll give you an example. Example 1. In this case, U is the open set U of R to the n. In this case, U is the whole real line. The initial time is 0 and the initial point in this real line is also 0, and the vector field is given as ft comma x is equal to tx to the 1 over 3 for all tx in R2. Now we try to find a solution to the IVB dx over dt is equal to ft comma x and x0 is equal to 0. This is the IVB that we are considering. Okay. Now we approach the problem by separation of variables, which leads us to dx over dt is equal to t times x to the 1 over 3, which gives us dx over x to the 1 over 3 is equal to t dt. Now integrating on both sides, we have 3 over 2 x to the 2 over 3 is equal to t square over 2 plus c prime. Okay, which gives us 3 times x to the 2 over 3 is equal to t square plus c with a suitable constant c. For a suitable constant c, I can write it as t square plus c. And now I plug in t equal to 0 and the value of x corresponding to t equal to 0, that is x of 0 is equal to 0, right? If I plug in these two values here, I immediately see that c is equal to 0, right? Now, which gives us the solution xt to be equal to equal to 1 over 3 to the 3 over 2 t cubed, right? In other words, I have 1 over xt to be equal to 1 over 3 times square root of 3 t cubed for all t in the set of real numbers. So this is the solution. Okay. In other words, this solves the IVP3. Solves the IVP3. Okay. So another thing to note in this context is that xt to be identically equal to 0, that is xt is equal to 0 for all t in R, also solves the IVP3, right? So if you plug in xt to be 0 identically, this equation will be solved, right? So it means that the uniqueness of the solution to the IVP that we mentioned earlier of this form is in general not guaranteed, even though the vector field is continuous in the neighborhood of our initial condition. Okay, this is important to know. So we'll discuss later under which condition the uniqueness of such initial value problems will be guaranteed. Okay, now let us move to the definition of flows first. Okay, now we'll define flows of a vector field. Okay, to be more precise, we want to define flow of a vector field. Let a vector field f from I cross big U to U, with I being an open interval containing 0 is given. Containing 0 is given. Okay, this vector field is given. The flow of this vector field f is a map theta from a domain D being a subset of I cross U to U which assigns to each point t comma p in this domain D the value of UPT, where UP from JP to big U is an integral curve of f that solves the following IVP. IVP given by the same old IVP, dx over dt is ft comma x, and x at 0 is p. Okay, all right, this is what we call form. Okay, so note during this definition we have assumed that the interval of existence Jp is from where the integral curve is defined. I mean that the integral curve UP is a map from JP to U, and it is assumed that this integral curve for this integral curve UP, both 0 and t, they belong to this interval of existence JP. So thus, according to this definition, we see that theta evaluated at t comma p has to be up, this is small up at t for all t comma p in the domain of the flow. Okay. Alright. So we'll be given a vector field first, F, from I cross U to U, and the flow of that vector field will be a map from the domain D to the open set U, so that the image of the flow map should be given by the integral curve that solves this initial value problem. Okay, so this is the definition of the flow of a vector field. Now, there goes an important remark of following this definition. Which tells us that there must exist at most one integral curve UP through each point P of the open set U. So big U, right, is an open set of R to the N. Through each point P of big U, there must exist at most one integral curve through each point P in U, so that TP is in D. There must exist at most one integral curve UP of F. Why? So this is the situation. There must exist at most one, so that this map theta is well defined. Theta is a map, right? You remember that the definition of theta, it was given by theta at t comma p is u of p at t, right? Okay. So if there were two distinct integral curves, UP and VP, through the point P at a given time t, we would have theta at t comma p to be both of them, right? Okay, so for the same value of t comma p, you would have two different values. We'd have two different values of u. That way, theta would no longer be a function. So in order for us to make theta a function, we must have at most one integral curve UP going through each point P of U, so that t comma P is in this domain T. Okay. Now, as pointed out in example 1, the IVP, the initial value problem IVP2, is not always guaranteed to admit a unique solution, right? We have already discussed it. We have already seen it in example 1, that the solution that solves IVP2 is not unique. We'll see in detail later that uniqueness of this integral curve going through a point P integral curve integral curve going through the point T0 P0 belonging to I cross big U. Okay, so the uniqueness of this integral curve going through this point is guaranteed for the case where, in addition to the continuity of this vector field F, U, so in addition for the is guaranteed for the case in which one has continuity of this vector field around T0 comma P0 plus some local Lipschitz condition is met. Okay, so remember that we talked about the sufficient condition for the existence of the integral curve, and that was that we needed this vector field to be continuous in a neighborhood of the point T0 comma P0, the initial point. Okay. Now, if we want the integral curve to be unique as well, we have to add an additional condition, which is the local Lipschitz condition. So we'll now describe this local Lipschitz condition in detail, okay, by means of it. Okay, so before giving the theorem of uniqueness, we'll first discuss about this local Lipschitz condition, okay. So let me describe this local Lipschitz condition first. So why do we need local Lipschitz condition? Because we want the integral curve to be unique. Integral curve solving the IVP should be unique as well. It should exist, and it exists because of the continuity of the vector field around the initial point. Now we add some additional condition, which is a local Lipschitz condition, and then we'll see that this integral curve not only exists but also unique. Okay, and what is this Lipschitz condition? So here it is. There exists a ball of radius r0 around P0 denoted by B of P0, B of R0 about P0. Okay, such that the closure of that ball is contained in the open set U, big U. Okay, so we are given that big U thing, which is an open set in R to the n. Now we have to prove that there exists a ball of radius r0 around p0 denoted by br0 p0, so that the closure of that ball is contained in U. Okay, now a side note which tells us that if you are not familiar with the closure thing, here the closure of the ball around p0 of radius r0, this denotes the closure of the open ball b of p0 of radius r0. We know all from the definition of this open ball in Euclidean space as the collection of all the vectors in R to the n such that the norm x minus p0 is strictly less than r0. That's the definition of the open ball centered at p0 of radius r0, right? So that the closure of that ball is defined as all those vectors of R to the n such that the norm now is less than or equal to r0. Okay, so in other words, intuitively speaking, if this was the open ball, centered at p0 of radius r0, include the limit points now, and this is the closure. Okay, if you include the boundary to the ball, that becomes the closure. Okay, so these are the given data. Okay, one must have a positive number delta 0 such that t0 minus delta 0, t0 plus delta 0, this closed interval has to be contained in the open interval I. Okay, so we had this initial point earlier, p0. We must have this number r0, that would be the radius. Okay, the radius of the underlying ball. So we need this number. We need another positive number delta 0 such that this closed interval is contained inside the given open interval I. We need another constant k0, but this constant may depend on the initial point p0, okay, for which the following inequality is satisfied. The norm of the difference between ftx and fty is bounded by k0 times the norm of x minus y for all xy in the closure of the ball about p0 of radius r0, and the time has to be inside this interval. Okay, in other words, t minus the mod of t minus t0 has to be strictly less than delta 0. So it tells us that t is inside this closed interval, right? T0 minus delta 0, T0 plus delta 0. Okay. So we already discussed in the introductory lecture that okay, I need space. We discussed in the introductory lecture that this symbol norm of x denotes the Euclidean norm of a vector, denotes Euclidean norm of a vector x in this Euclidean space. That is, norm of x is equal to square root of x1 squared plus x2 squared all the way up to xn squared. Good. So associated to this vector field, we have this additional condition of Lipschitz continuity, local Lipschitz continuity given by what we have just said. So if we are given this vector field, there must exist three numbers. Okay, what are those numbers? R0. So we have this vector field ft comma x, which is a locally continuous vector field around this initial point t0 p0. Okay, then we need three positive numbers r0, delta 0 and k0. Okay, such that this is satisfied. ft comma x, ft comma y, we take the difference between these two values, two vectors in R to the n, and take the norm of this guy, and this has to be bounded by k0 multiplied with the norm of x minus y for all xy belonging to the closure of the ball around p0 of radius r0. Okay, here comes this first positive number, and t belongs to this this closed interval, right? T0 minus delta 0, T0 plus delta 0. Okay, so here is the other constant k0 and delta 0 is the second constant. Okay, so this is nothing but we want the mod of this number t minus t0 to be less than or equal to delta 0. So t being in this closed interval is synonymous to the fact that we want the mod of t minus t0 to be less than or equal to delta 0. Okay, so if this thing is satisfied, then we say that the underlying locally continuous vector field is also locally Lipschitz continuous. Okay, all right. Some more terminologies about a vector field, about a type of vector field in particular. An example of a vector field for which the local Lipschitz condition holds is a C1 vector field F Okay, so what is a C1 vector field F? That is a vector field. Remember the vector field that we gave in the beginning of the first lecture, in the first segment? A vector field is given in equation number 1 in the beginning of this first lecture. So if you don't remember, let me recall. Ft comma x1 x2 all the way up to xn, this is nothing but a vector, right, in R to the n. f1 t x1 x2 all the way up to xn is the first component. The second component was f2 t comma x1 x2 all the way up to xn, and the nth component was fn t x1 x2 all the way up to xn. Okay, so these are the component functions. Okay, for F to be a C1 vector field, okay, we want the partial derivatives of all these component functions to exist and to be continuous. Okay, so del fi by del t and del fi by del x j for ij from 1 to all the way up to n, they need to exist and they need to be continuous. Okay, must exist and have to be continuous. Only then we say that the underlying vector field is a C1 vector field. Okay, so I'm not going into the detail of this analysis. An example of a locally Lipschitz continuous vector field is a C1 vector field F. So now we know what it means by a C1 vector field, and we also know what it means by a locally Lipschitz continuous vector field. Okay, a C1 vector field is an example of a locally Lipschitz continuous vector field. Good. Now, a few important things that we need to do. I am going to list these important tasks. Okay. A few important things we need to do. We need to give a precise definition of the domain, okay? That we're not going to do, we will not do right now, maybe a little later. We need to give a precise definition of the domain D for the flow map theta, for the flow map theta. Remember that this flow map was defined as theta is a map from D to the open set U, right? Where D was a subset of I cross U over which the vector field was defined. Okay. It was defined, this flow map was defined by theta t comma p is equal to u p of t, where up is the integral curve that solves the underlying IVP. Okay, this is how we define the flow of a vector field. So we need to define this domain curly D, okay, very precisely. This is something that we need to do. This involves knowing that each integral curve UP so this involves knowing that each integral curve UP through P in big U is defined on a maximal interval of existence JP containing T0, the initial point. So what does it mean by maximal interval of existence? It means that this JP contains any open interval containing T0 on which an integral curve satisfying the initial value condition is defined. Okay, and there is no other interval that contains JP satisfying this situation. Okay, this is the maximum interval of existence. Okay, so the second point being, we also want the flow map theta from D to big U to be continuous. This has to be continuous. We want this. This will require proving. So when we try to prove this, that when we try to prove that the flow map theta is continuous, we require continuous dependence on initial conditions. So we have the initial conditions that U of T0 is equal to P0. So we'll discuss the continuous dependence on this initial conditions, and we'll define what it means by continuous dependence on such initial conditions, and we'll give some results on the continuous dependence on such initial conditions. Okay, and these results need to be stated in order to prove the continuity of this flow map. Okay, we'll state all these results. On some occasions I'll sketch the proofs. Okay, but I'm not going to go over the proofs in detail most of the times, in order to save time, and partially because not you are all well equipped to go over the proofs in great detail. Okay, so these are the things that we are going to do in the following lectures. So now I'm going to state the first theorem of this lecture, which sheds light on the local existence and uniqueness of solution to the initial value problem that we discussed earlier. Okay, theorem 1. So let me name the theorem by local existence and uniqueness theorem. Uniqueness theorem. Let I be a subinterval of R, meaning that, well, I is a subset of R, which is of course an interval, an open interval, be an open interval, and U being a subset of R to the n, be an open set. Let T0 P0 belonging to I cross big U, and suppose that the vector field F from I cross U to U satisfies a local Lipschitz condition at T0, P0 given in equation 5. So have a look at the notes. You'll see equation 5 is what tells us equation 5 is the local Lipschitz condition that we discussed earlier. Okay. So I'm not going to write this local Lipschitz condition again, so I'm referring to equation 5. Okay. So we want this vector field F to satisfy the local Lipschitz condition at T0, P0 given by equation 5. If this is the case, if this vector field satisfies this locally continuous vector field also satisfies the local Lipschitz local Lipschitz continuity condition at T0, P0, then there exists a positive number called delta and a C1 function. We know what it means by a C1 function, right? A function for which all the first order partial derivatives that can exist and they are continuous is called a C1 function. A C1 function U from T0 minus delta to T0 plus delta, this open interval to big U, that solves the following IBB. dx by dt is equal to ft comma x, and x at t0 is equal to p0 over the interval T0 minus delta, T0 plus delta. Okay. So I did not write it explicitly that this C1 function is unique as well. Okay. This C1 function is unique as well. Okay. So about the local Lipschitz continuity, see that when you have this vector field F to be Lipschitz continuous locally, you have this thing happening, right? as we discussed earlier. This guy is bounded by this number times the norm of x minus y, where both these vectors belong to the closure of the ball centered at P0 and of radius R0. Okay, and these times they satisfy this condition, right? Okay, so we must have these three positive numbers R0, delta 0 and K0, depending on P0, of course. They will satisfy this thing, and then we say that the underlying vector field is locally Lipschitz continuous about T0, P0, right? Okay, this tells you that the derivative in the second variable xy, this is the second variable, the derivative in the second variable is bounded, is locally bounded. Okay, so this is what Lipschitz continuity tells us, right? So it's not like the differentiability. It also tells us that the derivatives are bounded. Okay, so that's pretty much it. I think I'll stop here, and in the last segment talk about extension of solutions. Okay, thank you for attending this second segment.